This instrument is called a Jacob's ladder. Notice how the spark discharge between the two poles rises to the top of the ladder. Can you think of a good physical explanation as to why the discharge occurs and why it rises? In this video, we'll focus on developing scientific explanations for physical phenomena. The outcomes of this session are to develop a culture of scientific reasoning amongst the learners, to use Coulomb's law to explain the oscillation of a charged sphere between two charged plates, to use Coulomb's law to calculate the force between two charged objects, to understand the difference between an open-ended activity and a closed-ended activity, and to understand that different people solve problems in different ways. So how does the discharge in a Jacob's ladder work?
Between the two poles is a big potential difference, and hence an electric field in the space between them. Now the charge is trying to move from one pole to the next to discharge through the air. In so doing, it's ionizing the air, pulling the electrons off the atoms, and where the two poles are closest together, one gets a discharge. This movement of current through the air causes the air to heat up, and heated air rises. So as it rises, it provides an easier path of discharge for the current, and the discharge happens higher. And so it goes on until it reaches very high in the Jacob's ladder apparatus.
At Inanda Seminary in KwaZulu-Natal, we came across a science teacher, Mrs. Buthelezi, demonstrating an experiment to her class.
This morning we are going to have an experiment on electrostatics. We have a power supply.
The learners are warned that they'll be working with a potential difference of 5,000 volts.
That's very high, so you mustn't come close, it's dangerous.
The experiment consists of a pith ball suspended between two oppositely charged plates.
I'm going to put the instrument on, you make your observations. There I'm putting on the instrument. Now, you make your observations, then you must be in a position to explain why is it going that side and that side when the plates are differently charged. You've made an observation. Now you go to your groups. You go and sit down and predict.
The learners are asked to work through a worksheet that requires them to explain why the ball oscillates and then also to find out what affects the frequency of oscillation of the ball.
To the ball, that's right.
The teacher walks around the class monitoring the progress of the different groups and helping them by asking relevant questions.
Positive. Now that I wanted my students to identify the relationship between the forces and the charged bodies so that they can understand Coulomb's law. Because otherwise, without the practical investigation, students tend to just memorize the formulae, which are not meaningful to them. Now you take a neutral thing, you put it
in this activity, the teacher has given her learners an open-ended problem. There's no one correct answer, although the reasoning that each group gives to reach their answer must be physically correct.
The ball is neutral. It's got equal amounts of charges, positive and negatives. So when the power supply is turned on, the positive charges from the ball will move towards the negative charge of the plates. And then these positive charges from the ball will move to... No.
The positive from the plates will move
to the negative side.
Negative.
Yeah, and then so the negative ones...
Learners often have problems formulating scientific explanations for physical phenomena.
We grow up with our own observations and thinking, and we form those, and then we have problems shifting from what we think we know to explanations offered by science.
This problem is often compounded by the lack of resources in schools.
Where you have resources, though they are slow to get to something, they eventually do see what it's all about. But when we don't have resources, they find it very difficult to understand. Coulomb's law theoretically is very difficult.
How could teachers overcome these problems?
Some of the strategies we need to use is to explore initially the learner's preconceptions. So it's important that we find out what the learners know about the ideas in science Now, the scientific ideas are not very easy to come by. In fact, most of the ideas that we have are common sense ideas, and the scientific ideas are really the opposite of common sense. So we need to challenge those ideas, and one of the ways to do it is actually to ask learners to predict situations. And a typical experiment that learners or that teachers set up involves the predict, observe, explain experiment.
Referred to as POE, learners are first given an opportunity to predict the situations that occur. They will then do the experiment and observe the outcomes, and finally they will need to give an explanation for them. Here a learner explains why the ball oscillates.
The pith ball is neutral, ma.
Yes.
It's suspended between these two plates.
Yes.
Let's suppose the pith ball is closer to the positive charge plate.
Put it in that position.
Yes.
Right. What happens to them?
When it gets to the positive plate, there will be the negative charges will attract to the positive plate.
You no longer have even distribution.
Be in excess of negative charges.
Once these get in contact, actually touch, what happens then?
There will be an equal distribution of the positive plate, and there will be an excess of
which charge in this case?
Of the positive charge.
So this whole thing now will be
positively charged.
Positively charged. Can it remain here when it is positive?
No, it will repel, because equal charges will repel each other.
It came from here now with an excess positive, right? So it is positively charged all over as it's coming now. What happens when it actually gets closer?
When it gets into contact with the negative plate, there will be equal distribution.
No, but of which charge now?
Of the negative charge.
Now it's negative. Can it remain there?
No, it will repel. It will repel back to the positive charge.
You want either to make it move faster or you want it to move slow. Argue out what could be changed.
Prediction also helps the teacher.
It helps you to understand how they think, whether they are in line with what you are expecting from them. Because if you don't just expect them to wait for you to give them the direction, then you are not even able to pick if there are any misconceptions on the way.
Use Coulomb's law because it says that force is inversely proportional to the square distance and directly proportional to the product of the charges, so we can.
So which means if we decrease the distance, we
increase the force between, and then
so
if
we have to
maybe increase the charges and also increasing the force.
You have made your predictions. Now come close again.
Generally, learners have predicted that changing of potential difference or the distance between the plates will affect the oscillation speed. The learners will now find out whether their predictions are accurate. The teacher begins by reducing the distance between the plates.
So the smaller the distance, the higher the force it experiences. That is why it is moving faster. Let us now increase this distance.
As the distance is increased, the oscillation is slower.
You increase the distance, you decrease the force. Let us reduce the voltage.
Let us bend to him. It's moving slower than before.
So it's experiencing how much force compared to the
Less
original?
force.
Less
than the previous.
Did you predict correctly? Yes. You know your physics.
Learners explain their observations by applying Coulomb's law, which states that the force between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. In this activity, the teacher has given her class a closed-ended activity. This is a traditional physics textbook problem. There's only one correct answer.
We gave them an application to solve problems using the law now, hoping that the students now know the meaning of Coulomb's law.
The first question requires learners to explain the meaning of the term inversely proportional when relating to Coulomb's law. Learners go to the reference book.
If you decrease the distance, you increase the force. If you If you increase the distance, you decrease the force.
Increasing the force decreases the distance by that square factor.
In the next question, learners are required to sketch a graph showing how the force between 2 + 1 microcoulomb charges changes as a distance separating the charges changes from 10 to 100 millimeters.
Means you know what this kind of graph means.
In most cases, the learners have drawn an inversely proportional graph but have not included the figures.
From what distance to what distance? Yes, then find the forces for those values.
The teacher demonstrates on the board.
What does Coulomb's law state?
Force is equals to K, which is a constant, Q1, Q2 over R squared.
The teacher substitutes the distance for 10 millimeters and 100 millimeters and gets to an answer of 90 Newton and 0.9 Newton respectively. She will then plot this on the graph.
If you say your 0.9 is here and your 100 is here, then roughly that is where you are going to put your point. If you say your 10 millimeters are here and the force is 10 newtons, that is where you have your point for the force. And then because you know the shape of the inverse proportionality, it's not a right angle thing, you draw a smooth curve. Yes.
In this question, the diagram shows two charged objects arranged so that the smaller object has charge Q1, a weight of 20 Newton, and is tied to a piece of string attached to the ground. It is attracted upwards to the larger object with charge Q2. Learners must draw all forces acting on the smaller object. After learners have had a chance to discuss this in their groups, the teacher reports back to the class.
What force is that?
It's electrostatic force.
The electrostatic force, that one. And I'm showing here...
It's a weight and a tension.
The tension that the spring, that the thread experiences and the weight of the object.
In the next question, learners have to calculate the tension in the string. The teacher begins by using Coulomb's law to determine the electrostatic force. She then moves to tension.
It will have to be the electrostatic force minus the weight of the small object.
The figures are substituted into the formula.
20 giving you 80 Newton.
The two activities shown in this lesson highlight the differences between problems in physics. In addition, teachers must remember that different people solve problems in different ways. The use of open-ended and closed problems by the teacher can help in this regard, but has its own challenges.
It is difficult to assess open-ended questions than straightforward traditional ones, because there you have your definite answers down. Here you have to try and find out what the pupil is trying to lead to. There may also be a problem of expression. The child may know what he wants to say, but the problem of expression causes a deviation at times.
Hi everyone, we have watched the video, and at the studio today we have Dale, Andrew and Lolo. We are going to be discussing the lesson that we have just observed. Forces becomes a very difficult concept to teach at that level. How would you help the teacher to teach a concept like forces?
I would say that the students have picked up the concept of forces earlier on. They seem quite comfortable with it.
Mm-hmm.
And they've probably done it in mechanics in grade 9, again in grade 11. But what is helpful is to always remember that a force is an interaction between two bodies. And so I think teachers should be consistent in always mentioning both of the bodies that are involved.
Mm-hmm. And I think the teacher has done well by actually showing that in her demonstration, the two forces that was there, and then she had the swinging ball. Do you have anything to add?
I think just as Dale said, that the swinging ball for the learners was very easy for them to see the relationship between force and the swinging ball. In fact, it was almost spontaneous, which again confirms what Dale said, that they obviously had grasped this concept very well. So this is not a concept that she had to go back to reinforce. And so I think she took off just where the learners were, and so she was very much in sync with where they were and developed it from there.
Mm-hmm. Then let's further, Lolo, look at the social construct. Here we're seeing a teacher teaching the learners to think and to solve problems. Could you relate some of the things that the teacher did in order to encourage the learners to think?
The educator asked them to predict the results and let them observe. So through their observation, they were able to explain the law.
She allowed them to work in groups and discuss this, you know, and so that I think is one of the critical outcomes that we want to have, isn't it? That learners should be able to work with others, to debate issues, to think about issues, to predict, you know, and therefore this is very much in line with the scientific process. So I think it was very good that she engaged them in that way.
Mm-hmm. And one of the things that the teachers did on the video was to actually engage the learners into two types of activities, open-ended activities and the closed activities. Can we maybe look at the value of open-ended activities in the science lesson?
I think there can be too much worry for learners about getting the right answer in a closed activity. And so an open-ended activity is nice because all ideas are worth something. And they get to think rather than focusing on what's the right answer.
Mm-hmm. And in doing that, the learners were engaged in discussion and they were talking and responding to the teacher's question. How do you feel about that in the case where the learners are actually explaining and trying to discuss themselves without the help of the teacher?
I thought it was really nice that they got so much opportunity to talk science. And it was nice that they got an opportunity first in small groups, which are less threatening, and then after that talking to the class as a whole, which is a more threatening situation. But there were lots of opportunities for them to talk science, and that's how we develop our ideas, is when we get a chance to talk about them.
Talking science means they're engaging with the issues, which means they are active participants in the process of constructing knowledge, you see. So knowledge is not just given to them as if they are tabula rasas, you know, blank slates, but they are actively engaged, and therefore there's a sense of ownership of this knowledge. So at the end of the day, I believe that the concepts will truly precipitate because they were engaged in it and they were involved, they constructed it themselves, they were actively involved in the process.
And one of the things that we have seen on the video was the teacher writing sketches and diagrams on the chalkboard. How do you think the chalkboard was used in this case? Lolo?
Very efficiently, the learners were able to observe and interpret what was seen or what was written on the chalkboard. So I think their skill of interpreting ideas was also developed.
And also there is a misconception that in OBE a textbook is not that important. But we saw the teacher there engaging the learners in consulting and making use of the textbook in order to consult and see some of the references. How did you find that?
Yeah, I thought that was great. The role of the textbook changes in OBE. It becomes a resource rather than the thing that's telling you what to do.
Is there anything that you enjoyed in that lesson or something that you'd like to comment about in that lesson?
Yes, I mean, you know, with obviously limited resources, you know, I think it was good that she actually did that as a demonstration. Also something that I found very interesting was the fact that she pointed out some of the dangers, or rather not the dangers, yes, and precautions that one needs to take in working with scientific equipment. You know, and I think that is sometimes an attitude we need to inculcate in our learners, that, you know, there are certain rules and regulations about how you conduct yourself in a laboratory. And again, people have thrown the baby out with the bathwater and have said that sort of thing doesn't count in OBE. But you see, there are many misconceptions about OBE. And I think this is one of the things that need to stay. There are laboratory rules, there are precautions that we need to take. And sometimes it's just practically impossible for the learners to do the experiment themselves. And therefore, an engagement like this is very useful.
And also, the presentation skill for the learners was also developed. They were given enough chance to talk within the group as well as independently.
True.
If that class was a very small class, so if the same teacher had to teach a bigger class, do you think she should change her method of teaching the same lesson? I mean, there were very few kids in that class as compared to the township classes where we have a lot of learners in one class.
Yeah, I think the strategies would be better actually, because first of all, she did she demonstrated. She had the equipment set out there. The equipment was visible for the learners to see. She demonstrated very well. She asked them to take down, to note what they saw and so on, and then to break up in groups. Now, if she had a bigger class, I mean, you know, the logical thing to do would then to have maybe more groups, you know. So that would be an obstacle, I think, the challenge that you would easily be able to deal with.
Or maybe the educator could rearrange the groups. Say, one group, one learner from each group should mix with the others for them to share what was happening. In that way, she's covering everything that is happening in each group.
I think group work is very important in a large class because there everybody gets a chance to have their say. Whereas in a large class, each individual's got even less chance to actually say something. And there's an opportunity for peer teaching that happens. And in that way, the teacher's load is lightened because students are helping each other.
The teacher kept on guiding the learners. As she was plotting the graphs, she kept on guiding the learners. Do you have any comments about that?
Yes, I think she was guiding them very well. In fact, maybe something I would like to pick up on is her technique that she was using, the question and answer technique. Very well used. You know, you can tell she's a seasoned teacher. And she allowed enough time for the learners to respond, you see. But also, one of the things that I perhaps would add to that is that she should maybe ask specific learners to give specific responses, because there were times when she was addressing her questions to groups, and you know, and the whole group responded, and it's so easy for people, learners within the group, to get away with that. But if you ask individual learners, you are able to get their response, and you're able to deal with misconceptions and issues that have come out of that. So she could have used that, but I think she used the question and answer technique very well. She probed them, she developed them, and she used the blackboard excellently to reinforce their answers and to develop the concept. So I think that was very well done.
What do you think about the scientific language and the calculations that the teacher did on the board?
Yeah, I think she was quite good about using scientific language carefully, because in science we use words with more precise meanings than in everyday English. But she also allowed her learners to express things in their own way. She didn't keep correcting them, and I thought that was a good thing as well, because it's a process. They'll get there.
Actually, that was based on the open-ended activities, where she just threw out a question and the learners were asked to respond anyhow, and therefore she was in a position to pick up the misconceptions.
Yeah. I just want to say that sometimes I find that with the group book, when the learners are discussing amongst themselves, that some teachers tend to be hesitant to allow them to discourse in the vernacular. Now, I know that is very debatable, and I want to touch here on a hot potato issue. But I think language is an issue, and science is a language of its own. But the whole issue of language, I think, perhaps in this case, we should say that when there is an open-ended question, learners should be given some degree of latitude to be able to discuss some of these issues in their own language. And I find it just adds more richness to the whole thing. And teachers who are obviously familiar with the language and so on can use that to further deal with misconceptions and to develop proper scientific concepts.
I think that is all we had for today. And thanks, Lolo. Thanks, Andrew. And thanks, Dave.
Thank you, Tim.
Thanks for watching, and bye-bye.